We're going to take a look at substitution for double integrals and triple integrals. Now previously, if you had an integral from a to b of f of x dx, the kind of thing we do to substitute is we'd figure out u equals something in terms of x, but we could also, if we're lucky enough, write x as something in terms of u. And if a is, so a here is an x value, so it's written right in that same spot. So sometimes your substitutions reverse nicely. So a equals g of c, b is the value of g of d for the appropriate values of c and d, and you'll have an integral with u from u values c to d of f of g of u. So you'll end up replacing the x here with g of u, and have then g prime of u du. Now this will all feel a little bizarre, it'll all feel a little backwards from the way you normally do things, but all the notation does end up working out. Let's just point out this part right here. This is g prime of u, or of course we can write this using Leibniz notation as dx over du. Now why, okay, the u there because the variable is u, and then why an x here? Well, because x is g of u. The other thing to maybe note right now is that this entire part right there, maybe we'll just write this over here, that g prime of u times du is, well, this first part, g prime of u, is replaced with dx du, and then we have still a du to copy, so this ends up being dx. So the point is this entire underlined part here would be dx. Now, this seems a little perhaps off just in terms of the role of the variables seeming to be swapped. What I'd like to do is basically, because it's going to set us up better for what we're about to look at in a moment, I'd like to write an integral from 2 to 3 of, and this is where things already start getting feeling a little unusual, u to the fourth e to the power u to the fifth plus 1 du. Now normally we're used to the starting integral problem being written using x's, but we're intentionally writing things let's say backwards in a sense. So when we're done with this example, if you want to in your mind switch all the u's for x's and x's for u's, fine, but using the notation in the way we're about to do it is going to better set us up for what we're about to do. So normally instead of doing a u substitution, we're now going to do an x substitution. So just kind of roll with this for a second. If you maybe the roles of the variables seem a little swapped, but I think you'll follow what we're doing just fine here. So an x substitution. We'll go ahead and do what you would expect here. That x would equal u to the fifth plus 1, and then dx equals 5u to the fourth du. And if u is equal to 2, then x is going to equal 33. We won't go through all the, 2 to the fifth plus 1. And if u is equal to 3, then x is equal to 244. Just to match up our notations with the generic example up there, we're just going to point out that here g of u is equal to u to the fifth plus 1. So with those substitutions in place, because the integral we're about to write down, let's actually put in a little more detail here and just put, just for clarity's sake right now, u equals 2, u equals 3, and then we'll have here, I know there's no 1/5 in the integrand over here, but I just inserted a 1/5 because I'm about to insert a 5 as well. Then e to the x to replace e to the u to the 5 plus 1, and then times, let me just move the 5 over, still u to the fourth here. So I'm just going to write that as u to the fourth du, the whole point being that this entire part right there is dx, right? Which we see right here. Okay, and then, because we're about to replace this with dx right here, now the bounds of the integral should be x values, which is why we computed these over here. And we'll have integral from 33 to 244 of 1/5 e to the x. And then, of course, this computation continues, but we're going to pause it right here. So I know that we're more used to seeing the initial problem have x's and then the new simplified version of the problem having u's, but we've swapped the role here of these two. Couple things to notice, though. So please notice that we had substituted x equals u to the 5th plus 1, and then dx over du is equal to 5x to the 4th. I mean, that we saw right here. If you just divide both sides by du, you'll have dx over du is equal to 5x to the 4th. But the reason to point this out is that we have, sorry, not 5x to the 4th, 5u to the 4th. But the reason to point this out is that this appears right there. Yeah, so the point is that we really have that dx ended up being 5u to the 4th du, where this 5u to the 4th is truly g prime of, so if we use this notation here, if x is equal to g of u, and so that means, by the way, that g of u, just based on over here, is u to the 5th plus 1, then we actually have that dx ended up equaling g prime of u du, as we saw was what dx equals in general right over here. So going from just trying to be very consistent in terms of notation, even if it all feels a little backwards, going from integral 2 to 3 of u to the 4th e to the power u to the 5th plus 1 du, going from this integral to the integral that we ended with over here, integral 33 to 244 of 1/5 e to the x dx. This is an example of substitution. It's just sort of backwards again, because we normally start with x and end with u, right? So let's just talk through this, that the old variable was u, and the new variable is x. So we needed to compute in doing this, we needed to compute dx over du. Let's point out here. So yeah, here it was, right? 5u to the 4th in this example. The key thing being that x was the new variable, and u here was the old variable. And we also took the old interval, and the old interval, which was u had to belong in the set 2 to 3, so that interval. This corresponded to the new interval, where x had to belong in the set of reals between 33 and 244. Okay, now the key feature of what makes substitution work, this was true in the past, was, so going back to the usual integral, starting with, if you're starting with integral, you know, a to b f of x dx or whatever, but the point is, if you're starting with an integral that has a dx here, you have to replace dx. Okay, so for example, in what we just looked at, if you had the setup where, you know, the substitution that would work out for your problem was x is equal to u to the 5th plus 1, let's just say that was a substitution that worked out. I mean, I'm trying to go backwards. Say you had this problem, for instance, and you want to go backwards to this, which seems a little strange, but let's just go with it. Then dx over du is equal to 5x, 5u to the fourth, excuse me. So then solving for dx here, you just need to multiply by du on both sides. So dx equals 5u to the fourth du. And so then the point is this dx, replace dx with this. And by this I mean that stuff here. And then let's just point out that this part here, 5u to the fourth, this is in more generic situations, this is dx over du again. Now, the thing is, we want, in just a moment right now, we want something similar. We want something that's going to be similar or plays the same role as this dx over du does. So in this example, 5u to the fourth, generically dx over du, but what's going to play that role for a double integral? So in other words, what about if you're given integral 0 to 4, integral y over 2 to y over 2 plus 1, okay, and the function to integrate, say, is 2x minus y over 2 dx dy. What about in this situation? Now, we could do the integral directly, but what does substitution look like? And here's what we're going to do. It's going to look a lot like what we see here. We're going to, because it's more convenient for what's going on, try to write old variables like x and y in terms of new variables. So if x equals something we're about to write down, and y is equal to something, okay? And so just like over here, x was the starting variable and your new variable u appears over there. So x is written in terms of u. Here we're going to have x written in terms of, well, not just u. You can't just get away with one variable. We're going to need two variables. So this is going to work out for us. X is equal to u plus v, and y is equal to 2v. Now, your first thought is going to be, how did you come up with these substitutions? But think about it. Let's hold off on that. We got to just see the process all the way through. This would be just like when you first learned substitution for integration in your first calculus class. Your natural question was, where did you get those substitutions? But you got to just see the process all the way through first. So we want to replace dx dy. And why this? Because over here in the past you would have replaced dx. Okay, and what are we going to replace it with? We're going to replace it with, and you got to excuse the notation for a moment. We're going to dig through all this stuff. It looks like absolute value. Okay, it looks like a fraction. You see that partial derivative symbol, but something's going to look a little funny here. Okay, partial derivative of x and y with respect to the variables u and v. There's a lot to dig into here, so just hang on for a second. Okay, du dv. So if we go back up here, this part, 5u to the fourth, is being played by that part. And then du from before, it's now du dv. All right. Now, the process of selecting x equals something, a new formula that has, a formula that has new variables u and v, and y is a formula that has new variables u and v. I guess this formula only has v and no u's, but this is going to work. This should just be called substitution, and it could be, but this is just also called, by our book anyway, this is called a transformation. So we are seeing an example of a transformation. So now the next question is, well, what the heck is this part right here? What is this? Let's go with it. What the heck is this? So let's introduce the new concept. Here, it's going to help us do substitution, and then we will do, of course, full-on examples. But first of all, let's clarify what this thing is by introducing this definition. So if x is equal to g of u comma v. So x is written as a function of two input variables u and v. and y is written as a function of two input variables u and v. So let's say h of u comma v. So that's the setup to start with, right? So we have a transformation, as it was called up here. So this new thingy, right? So then the Jacobian of the transformation is, well, here's the notation. I'm just copying from above so that we introduce the notation in the definition as well. Okay, so just copy that. What is it? It is actually a determinant of a matrix. So remember, for a determinant of a matrix, we can just draw vertical bars, and inside we're actually going to have partial derivative of x with respect to u, partial derivative of x with respect to v, partial derivative of y with respect to u, and partial derivative of y with respect to v. So you'll note that what happens is in the rows, the numerators are partial of x and partial of y, and then in the columns, look at the denominators. It's with respect to u and with respect to v. So there's the definition. Let's compute an example, and then we'll close off this part here. Okay, so example. If you start with, starting with, let's just say given what's above at the top, x equals u plus v, and y equals 2v. Okay, so then let's go ahead and compute the Jacobian partial xy with respect to uv. Okay, so this u plus v thingy is our g of u comma v, and 2v is our h of u comma v. Right, so let's just compute what we'll get. Let's just copy down maybe this. You know, in the future you might not copy down, but partial of x with respect to u, partial derivative of x with respect to v, partial derivative of y with respect to u, partial derivative of y with respect to v. And we'll just we'll compute the partial derivatives. Okay, so partial of that u plus v with respect to u should be 1 plus 0. We're just going to write 1. Partial of x with respect to v should be 0 plus 1. We're just going to write 1 again. And then partial of y with respect to u, well, u doesn't show up, so the derivative there is 0. And then partial of y with respect to v is 2. Now let's just compute that determinant. So 1 times 2, so this 1 times that 1, minus, then this way 0 times 1. So minus 0 times 1, or 1 times 0. Okay, so 2 minus 0, which is equal to 2. So there we've computed the Jacobian, but the usual way it's going to get used is the Jacobian is going to be multiplied by du dv. So that's what will replace dx dy. So in other words, just to follow up, what's going to happen for this problem, if we were to continue this problem all the way through, dx dy is going to become the computation we just did. So I'm just copy the notation here. Over partial uv, then du dv. So in this example, this part that we just computed became the number 2. So let's just put that in place, 2 du dv. Just one final word, just meant for anybody who is currently in or has taken linear algebra. If you haven't, this next part, just a little factoid, doesn't really help anybody else out, but it's just worth making a connection. So if you're in linear algebra, this transformation, the one that's being described right here, yeah, x equals u plus v, and y equals 2v. This is actually, we got real lucky that this is a linear transformation. Okay, so if you haven't taken linear algebra, it's just a little factoid, but let me note the following neat thing here, and note that if you took the matrix 1, 1, 0, 2 and you multiplied by a vector filled with the variables u, v, you would end up getting the column vector filled with the variables x and y. And it's kind of neat that, so this matrix can, in a sense, be thought of as a linear transformation. It's the matrix of the linear transformation, and then the determinant of that matrix appears right there. The determinant of the matrix is, in this case, sort of like a derivative.